Okay, good day everyone. All right. So, in this video, I want to talk about one of the past year paper, the most recent one, at least at the time of this video, right? Okay, it's going to be Pspm 2, 2020 and 2021. So this is going to be the second semester of the of your matriculation studies. All right. So in this particular semester, you've covered three main things, or at least three main themes, right? The first theme being electromagnetism, right? The second theme would be optics, right? This is where you deal with light and lenses and slits. And then the last of the theme would be modern physics, all right? So in this part one, we're going to discuss questions from the first theme, which is the electromagnetism block or theme, right? Okay, so this ranges from question 1 until 5, all right? And then question 6 will be on optics. Okay, so let's look at the first question, right? So let's look at the first question. Okay, so here we have a question from chapter 1, right? So this is going to be from chapter 1. I'm just going to write a note there. It's going to be chapter 1, and it's going to talk about electrostatic, right? Static. So just a reminder, electro refers to the presence of charge, and static means it's not moving. Okay, right. So let's look at the question. Figure 1 shows three fixed point charges Q1, Q2, and Q3, each given their respective charges. All right. And then, okay, so the first question would be sketch the electric force diagram on the charge Q3. All right. So very quickly, we can see from the diagram that, okay, we have a negative sign on Q3, we have a positive sign on Q1, so they'll be attractive. So we can just immediately draw a force diagram between 1 and 3. So that's going to be 1 on 3, right? So there's going to be electric force, Q3 being pulled towards Q1. And then I have, again, Q2 is positive, Q3 is negative. Again, it's going to be an attractive force. I'm going to have here F 2 on 3, right? So I can easily sketch out the electric force diagram, right? Electric force diagram, I will have Q3 here, negative Q3, and then I will have an attractive force towards 1, so that's F1 3, right? And then I have again another attractive force towards Q2 here, so F2 on 3, and then the angle between them is going to be 90 degrees, right? So that's all for the electric force diagram. We have labeled, okay, two main forces that Q3 experiences, right? Okay, so now what I want to look at is the second part of the question, right? Second part of the question, it's talking about calculating the total electric potential energy of the system. All right, so if you think about electric potential energy, that is a scalar, there's a scalar quantity. So generally we don't worry about direction. We do worry about their charges, the positive or negative of the charges, but we don't necessarily care about the direction because it's going to be radial in its nature. Okay, so it's going to be radial, so that means if Q1, the electric potential line or equipotential line, is going to be radial, so the further it is, the weaker it will be. And again, Q2 as well, you have electric potential, the further it is, the less that it feels, right? So total electric potential, just the whole system as a whole. All right, so we'll just consider the interactions of all, right, charges. So first we have, let's just have Q equals to K, right, and then KQ over R, right, KQ over R. So let's consider the interaction between Q1 and Q2, right? Q1 and Q2, and then their distances. So I'm just going to write down there R1, 2, right? And then now I'm going to consider Q1 and Q3, right? And then the distance between them, 1, 3. And then at the same time, I'll consider, so 1, 2, 1, 3, and I'll have 2, 3 as well. So Q2 and Q3. And then, of course, the distance between them. right? So once I have this, I can continue on substituting certain values to calculate their answers. All right, so I'll have K, I'll just simplify it as 9 times 10 power of -9. All right, and then I have Q1. So Q1, if we refer here, we'll have 12. All right, and then Q2 is just 3. All right, and then the distance between them, so Q1 and Q2 will be the square root. All right, I'll just write that down here, the square root of 8 square plus 4 square. Okay, and then I'll have the second part, Q1 and Q3. So Q1 and Q3, that's just 8 centimeters away, right? And then I'll have Q1 again, 12, and then Q3 to be -4, right? And then the last of it, which is Q2 and Q3. So Q2 will just be 3, +3, and then Q3 is going to be -4. All right, and then the distance between them will just be 4 centimeters. All right, so at this point, you might notice that I have taken out all the exponents, right? Instead of 12, this should be 12 times 10 to the power of -9, but I didn't do that. So what we can do, because we know all of this is going to have that exponent, we can actually take it out, right? We can actually write down there 10 to the power of -9, so this is going to be squared, right? And we can do the same thing for the denominator, all right? And I'll just write down that 10 power of -2, right? So if that is a much simpler way of doing things, okay? So if you key that into your calculator, what you'll get is approximately -4.48 microjoule, and that is going to be your final answer for this particular question. Okay, so it's a very simple way of just taking out all the exponents rather than writing them full, or what I mean by that is substituting every value including the exponents. Rather than doing that, I'll just take it out. All right, so it's a very simple multiplication, or just simplifying the expression. Okay, all right, so moving on to the second part of the question. Okay, I have a small ball with mass 25 grams. So 25 grams, I'll just immediately write it down here. All right, so 25 grams is going to be 0.025 kilogram, just for the simplicity of it. Has a total charge of positive 20 microcoulomb. Okay, is placed between two parallel charge plates. In static equilibrium, determine the magnitude of the electric field in the plates. Okay, so for B1, because it mentions static equilibrium, right? We know that the electric field is going to cancel out the weight or the gravitational pull or gravitational force, right, on the small ball, all right? So in order for that to happen, what we can do is we can rearrange. Okay, we know gravity is going to go downwards. Okay, so we want to arrange our small plate such that it produces an upward electric field. So you want the electric field to be upwards, and because this small ball is positively charged, in order for it to go upwards, we can have a negative charge at the top. All right, so my electric field will look like that. Okay, so if you were to draw the free body diagram for this particular ball, or for this particular situation, okay, let's say I have the ball here, and then I have my electrical force going upwards and my gravitational, or my weight, going downwards. Okay, so in order for it to have static equilibrium, all right, in order for me to have static equilibrium, I will have the electrical force being cancelled out by the weight of the ball. Okay, so again I have here QE equals to mg. Okay, so if you were to look for the magnitude of electric field, I'll just rearrange that, or bring the charge to the other side. I'll have E equals to mg over q. All right. So substituting the values, again, let me just remind you that substituting values and writing them down has marks for them. Okay. So 0.025 kilograms times G, which is 9.81. We approximated to 9.81. And then Q to be 20 microcoulombs. So times 10 to the power of negative 6. Okay. So again, if you key that into your calculator and let it compute, you'll have a value of approximately 12.26 kilo Newton per coulomb. All right, so that's your final answer for this part. Okay. Now, on the other hand, we can move on to the next part of the question. I'll write down here B2. Okay. Calculate the acceleration of the ball if it moves horizontally parallel to the electric field. Okay, so horizontal and parallel. So if it's moving horizontal, so I can have the ball over here, okay, parallel with the electric field, okay, I can have because this is positively charged, I can have here positive charge, and then I have a negative charge here, right? I have a negative charge there. And then at the same time, we should not forget that it is still influenced by the weight of the ball, right? So if I were to draw the free body diagram this time, I'll have the electrical force to the right? And then I'll have the gravitational force going downwards, okay? So as you can see, this is a very simple example. You can apply Pythagoras theorem, right? I'll just write down the SPT, Pythagoras theorem. I'll have the um, resultant force, so resultant force, okay, to be the square root of Fe square, so Fe square plus Fg square, right? Square rooted again, right? And I'll have the triangle that we know and love, right? A right angle triangle. Okay, so again I have Fe equals to QE, Fg equals to mg, right? Let's just substitute those values, and I have the resultant force to be ma, right? Ma. So I'll have ma equals to QE squared, sorry, QE squared plus mg squared, okay? Square rooted. All right. So now what we can do is substitute for the values. And at the same time, we have the value from our previous question, which is 12.26. So we assume that it's going to be the same electric field, same strength, same electrical field strength. Okay. What I'm left with is m times a equals to the square root of q. So what is q? Q is 20 times 10 power of negative 6, and then I have 12.26 times 10 power of 3, and then I square that, plus, right? So my mass will be 0.025 times 9.81, okay? And I square that, and I square root the whole equation, okay? And a, we can substitute those values. I have m as 0.025, right? So m is 0.025, all right? Once I have that, I solve for a, and a should be approximately 13.8947 meters per second okay? All right. Okay, so you can key all of that in. Again, you have marks for substituting values and then the final answer as well. Okay, so two very different arrangement of charged parallel plates, right? We can assume that this has the same electric field to do our computation for the second part. Okay, right. So again, let me just remind you that in this particular, in the first case, right, um, the electric field lines are vertical, right, opposing to the gravitational force or weight. And then on the second case, which is B2, we have the electric field being perpendicular, right, 90 degrees to the weight or gravitational force. Okay. All right, let's move on to the next question. Now, the next question is going to be on capacitors. Right. So let's read the question. An uncharged capacitor of 58 microfarads is connected in series with a resistor of 100 kilo ohm. Okay. So once I've read the first sentence, I can immediately start my calculation actually. So I can immediately calculate, because we know this about capacitors, I can immediately calculate the value for RC. So R is going to be 58 times 10 to the power of negative 6, right? And then I have a resistor of 100 coulomb. So 100 times 10 to the power of 3, right? So 58 times 10 to the power of negative 6 times 100 times 10 to the power of of 3, that would leave me a value of approximately, or not approximately, exactly 5.8. So again, because we're talking about RC, we can actually use their units. So R has the units of ohm, C has the units of farad, so I'll just use ohm farad for now because this is not our final answer. Now, continuing on, reading the question. Then the capacitor starts charging through the resistor. Calculate the time required for the capacitor to reach 30% of its maximum charge. Okay, so this this statement or this phrase, to reach 30% of its maximum charge, is very, very important. All right. Now we know the equation for charging is actually Q equals to Q naught, right, times 1 minus E to the power of negative T over RC. Okay, so Q is actually at any given time, at that specific time, whereas Q, right, is its maximum charge, right? Its maximum charge. So if it says to reach 30% of its maximum charge, we can convert this into an equation form to say Q over Q naught is equal to 0.3, right? And this number is actually equals to 1 minus E, right? E to the power of negative T over RC. Now, at this point, you'll see that the RC that we calculated earlier on comes in handy, right? Okay, so I'll have 0.3 equals to 1 minus E to the power of negative T over 5.8. Okay, so we can solve that equation for T, okay, to get approximately 2.069 seconds. So in 2.069 seconds, the capacitor will be charged up to 30% of its maximum charge. All right. So this point where you actually convert from sentence, right, from sentence into equation, which is this part. This part actually has marks, and in your examination, or at least in the marking scheme, this is what we call concept satu. It's a mark for your concept, for your conceptual understanding of what is happening, right? And then you have marks for substitution as well as your final answer, which is why they allocated 3 marks for this particular question, all right? So please bear in mind, even converting from sentence into mathematical expressions or mathematical equations has marks. So once you've done that, once you've read it, try to convert it or express it mathematically, all right? Because you never know, there might be marks in there, all right? Okay, now, so we've done chapter 1, we've done chapter 2 being question 1, question 2. Now let's move on into question 3, all right? So there's 2 parts for question 3. This particular part will be on Ohm's law, all right? Ohm's law. So this is on Ohm's law. In particular, this is looking at resistors in series as well as in parallel or in different configuration. Okay, so just a conceptual or a diagrammatic approach, right? So let's just have it being sorted in a straight line. Okay, I'll have R1 here, so I'll have R1 here, and then I have R2 here. Okay, so R2, and then I'll have R3, okay, and then the ends are connected to to the power supply, or yeah, to the power supply. Okay, so I can simplify this, right? If I were to say, okay, I have here R1, I can combine R2 and R3 into one capacitor. Okay, so this is R2, 3. Just remember that R2 and R3 are parallel to each other. Okay, and then once I have that, I can have an effective resistance. So that simply means it's going to be R1, 2, 3. Okay, now if you move backwards, right, if you move backwards, you can see that on the first instance, going from here to here, let's call that step 1. In step 1, you can write down that R1, 2, 3 is simply R1 plus R2, 3. Okay, because they're in series, right? If you go back again another step from R2, 3 to this one, so this is the second step, right? You can have R2, 3, because they're in parallel. I can immediately say that it's going to be 1 over R2 plus 1 over R3, and then the inverse of that. Once I have these two, right, I can substitute equation 1 into equation 2, right, to get R effective, which is simply R1, 2, 3, is equals to R1 plus 1 over R2 plus 1 over R3, and then the inverse of that. Okay, so that is how you can work out the equation for effective resistance. Okay, so now we want to solve for R effective. Okay, so let me just write down here again, just to remind you that the effective resistance is simply the R123. The R123 is just when you combine R1 and R23. R23 is when you combine between R2 and R3. Alright, so here let us just substitute some values. R1 being 10 ohm, and then I have 1 over R2. 1 over R2 is just 1 over 12. And then I have R3 being 5, so 1 over 5. And then the inverse of that. So you press into your calculator, what you will find is that your R effective is simply going to be 13.53 ohm. Alright, so that's your final answer. Alright, so working out this equation for R effective again gives you a mark for concept. Right, that there's a mark for concept, and then of course substitution, you get another mark, and your final answer with unit. Okay, I cannot emphasize it enough that with unit is such an important phrase, right? That what you do must have units. If you don't, it's not physics, it's math. Okay? So you will get your mark once you have all three of this, which is the equation for effective resistance, the substitution for the values, as well as the final answer with the correct units. Okay? All right, so let's move on to the second part of the question, all right, which is question 2, sorry, question 3A2. Okay, now they are asking for the potential difference across R3. So what that means is that if I were to take the reading and if I were to take a voltmeter and take a reading across these 2 points in the circuit, what would that reading be? Okay. Okay, so we want to think about this particular situation in a specific way, right? So if I have the positive terminal here and I have a negative terminal here, current will flow here and then across R1, go through this particular junction, and is split into 2, right? Split into 2. And then comes back in, goes through R2 and goes through R3, comes back in at this junction, and then travels back to the battery. Okay, so now I know, right, I know that I can have a simpler simpler diagram that looks something like this. So I can have a battery or a power supply and then the resistance, and that resistance is going to be approximately 13.53 ohm. So 13.53 ohm, and I have a power supply of 15 volts. Okay, so even from this simple diagram alone, I can work out the current that flows through this whole resistor. Okay, I can simply apply Ohm's law, V equals to IR. Now I tend to remind my students, you kind of have to know what V are you talking about, what I are you talking about, and what R are you talking about. So in this particular case, we have V of the power supply, I, so I label I1 here, or I total, right? I total here, and I have R effective. So R effective is simply the R123, right? And then I have P of the power supply, which is just the power supply given, and I total. So where is the I total? I total is going to be here, I total, before the junction. So if 3 ohm is going through here, it's not going to be the same as I2 and I3, right? I'm not applying Kirchhoff's law here. It's just plain. It's just based on our understanding of what current is, right? So we have a total current, right, that we can calculate. So I can rearrange those values. I can substitute the values. So my power supply will have 15 volts. I have my I total and I have my R effective. So my R effective is going to be 13.53 ohm. All right. So what I'm left with is that my I total is simply going to be 1.1087 amps or amperes, right? So that is my I total. What I don't know, right? What I don't know is I don't know, right? What is the current going through resistor of R3, right? The good thing is in a parallel system. So in a parallel system where I have R2, right, and R3, in a parallel system like this, in a parallel configuration, I know that my voltage through R2 and R3 is going to be the same as my voltage that goes through 3, just the just resistor 3. Okay, and my V23 is simply going to be my I 2, 3, which is the same as my I total, right? Multiplied by my R, which is my resistance, of 2, 3 combined. Now, in this particular case, I want to emphasize that because R1 and R23 are in series, therefore my I total is going to be the same as my I23. Okay, so even though they split off at junction A, they will recombine at junction B, right? They split off, some goes here, some goes here, the other one goes here, but at junction B, they'll recombine. Okay, they'll recombine at B. Okay, so I can work out what my what is my potential difference across resistance 3, right? Simply by assuming I23 is equals to IT. So I can calculate V3 and substitute for Vt, which is 1.1087, and my R23, which is simply 1 over 12 plus 1 over 5, and an inverse of that. Okay, and from there what I will find, my voltage or my potential difference across R3 is going to be approximately 3.913 volts. Okay, so there's a few things that there's a few concepts that you have to understand, which is the first one is that if you in a parallel configuration for both resistors you have their voltages the same. Okay, and then for a series configuration, you have their current values to be the same. Okay, once you combine those two ideas, then you can get the final answer. All right. Okay, good. Moving on. Here is a good question on Kirchhoff's law. So again, this is going to be Kirchhoff's law, the bane of all matriculation students. So much work, but I think this particular part is relatively simpler. All right. So how can we start? Okay, we can start by reading the question, right? So figure 3 shows a circuit consisting of two batteries. So two batteries, epsilon 1 and epsilon 2, and two resistors. So I have two resistors, R2 and R3. Calculate the value of I3 and R3. All right. So so Kirchhoff's law has two laws. Number one is the current law, and then the second one is the voltage law. Let us apply the first part, which is the current law. If I choose a junction, let's say here I choose at junction A, I apply current law. What I'll find is what goes in must come out, right? So if what goes in is 9 ohm, so again here I'll have I1 equals to I2 plus I3, right? So if I have 9 ohm here, 9 ohms, and I find that I2 has the value of 3, then I can most certainly calculate I3, which is simply 9 minus 3, which is just 6 ohms. Okay, so we found the first part, which is I3. The value for I3 is simply 6 ohm. Okay, all right. So now the second part requires us to choose a very specific loop. We can apply the Kirchhoff's voltage law to a specific loop, and then we'll find the value for R3. Obviously, it would be preferable if we choose a loop that includes R3, right? So let me just label this to be B, C, D, A, E, F, right? So which loop am I going to use? I am going to use, in this particular example or this particular solution, I will choose the loop of, right? The loop of B, C, F, E, B, right? So this is going to be my loop. How does that look like? All right, that looks like this. Let me just draw it out. I'll have like this, and then I have a resistor which is valued at R3. Okay, that looks fairly simple. I am going to ignore dA. Ignore dA. All right. So if I were to apply the Kirchhoff's voltage law, I will have epsilon 1 equals to I3 R3, because we only have one resistor, right? We only have one resistor. Again, let's just check for the loops. Okay, I have a positive terminal here and negative terminal there. So that means I will have a loop that goes clockwise, and my current values are clockwise as well. Okay, that makes my life much easier. Okay, so epsilon 1 has 18 volts. I3 is simply 6 amps. And then I have R3, which when you calculate, you will find R3 to have the value of 3 ohms. And that's my answer, which is R3 equals to 3 ohms and I3 equals to 6 amps. And that is how we apply Kirchhoff's law in this particular question for this particular year. All right. Okay, so we've done chapter 1, electrostatics. We have done chapter 2 on capacitors. We have done chapter 3 on Ohm's law as well as Kirchhoff's law. Now we can see that we move on naturally towards chapter 5, which is electromagnetic induction, which is where you can induce current as well as EMFs, electromotive force, from changing a number of variables. Okay, so let's look at the question right at hand. A 14 turns circular coil is placed on a paper which lies in 1.2 Tesla magnetic field pointing inwards to the paper. The coil's diameter changes from 22.5 centimeters to 7.2 centimeters in 1.8 seconds. Okay, so determine the direction of the induced current. So for A1, determine the direction of the induced current. All right, so as the area decreases, right, the magnetic flux, right, the magnetic flux decreases as well. Okay, so then magnetic field will be induced to oppose the decreasing magnetic flux. You apply to your right hand rule, what you'll find is that induced current will be clockwise. And that simply is the answer for 4A1. Okay. Why does it oppose? Well, that is based on Lenz's law as well as Faraday's law, right? Okay, so now we move on to 4A2, right? So 4A2, they're looking for the magnitude of the EMF induced in the circuit. Okay, now if we look at the equation for working out EMF, right, we can find that it's going to depend on the rate of change of magnetic flux, which is d phi over dt. On the other hand, we also know that phi is simply going to be NBA cos theta. in this particular case, B does not change, your angle does not change. What does change is your area. So your area has a non-zero change. So it means that your area changes. Okay. So what that means that for your equation is that your EMF is going to be equal to your negative NB cos theta, right? So this is going to be the first part. The second part is going to be your delta A over delta T. Okay, so NB stays constant, theta stays constant, perfectly fine, and then your delta A has some values, right? So again, let me just remind you that your area of a coil is going to be pi r square. Okay, so what that means is that your delta A is going to be pi times r final squared minus r initial squared. Okay, that's just a quick reminder. Okay, so now we can substitute those values. I'll have epsilon equals to, right, negative n is 14 turns, so 14 turns, right? My B is going to be 1.2 cos theta. Theta is 0, so cos theta is just 1, right? So this is just going to be simply 0. And I have my delta A. This is going to be a bit longer, so pi, and then my R is going to be, my final R is going to be 7.2 squared over 2 squared, okay, minus 22.5 squared over 2 squared. So that's my delta A. And then my delta T is going to be 1.8 minus 0. If you key that into your calculator, what you'll find is epsilon is equals to 0.333 volts. All right. Okay. So why do I have square on both sides? Because it's going to be R. This is going to be R square is equals to D over 2 squared, right? So that D means diameter. And I'll simply have 2D square over 2 square. I'll have to square both the numerator and the denominator. Okay, fair enough. All right, so moving on to the next part of the question, which is asking us to calculate the induced current. So the induced current if the circular coil resistance is 7.5. So I'll have R. I have R, I have epsilon. So that simply tells me that, okay, I can use Ohm's law. So Ohm's law tells me that epsilon equals to IR. Okay, so I is simply epsilon over R, right? Yeah, epsilon over R. I have epsilon to be 0.333 and R equals to 7.5. Okay, key that into the calculator, check if you have the right answer. Should be 44.41 milliamps, right? So I'm just applying Ohm's law at that point. Okay, so let's look at the second part of question 4. A circular coil of n turns, n number of turns. So we do not know what is the number of turns, right? But we do know that the current running through it is 9.1 milliamps, and we know that the inductance is going to be 15 millihenry. Okay, so we are asked to calculate, first things first, I'm the realist, but second, which is the magnetic flux linkage. So magnetic flux linkage simply means, let me just have a big phi instead of a small phi. I'll have big phi equals to n phi. Okay, so this is going to be related to your inductance or self-inductance, right? So my self-inductance is simply going to be N small phi over I. N and small phi just gives me a big phi over I. Rearranging that, right? Rearranging that, I can look for phi, which is, so phi is simply L times I. Substituting values, right? L will be 15 millihenry, so times 10 to the power of -3, and then I, which is 9.4 milliampere, so times 10 to the power of -3, right? And then what I will have for my magnetic flux linkage is 1.41 times 10 to the power of -4 Weber. All right. So that is my magnetic flux linkage, which is just the flux linkage through the whole, all of the turns of the coil, rather than a single coil. So small phi, single coil. Okay, big phi is all the coil, all coil. All right. Okay, now they give us a number for the number of turns. All right. So B2. Okay, I want to look for R, right? If I know what is N. Okay, so for a coil, right, you will have your self-inductance to be L equals to mu naught N square A over 2R. Okay, so R is just the radius that I can rearrange for. Okay, so I can rearrange this equation to have R equals to mu naught N square A over 2L. Now, the problem is that A also depends on R. So what I was supposed to do was actually to rearrange or to substitute values to remind myself the equation for A, which is mu naught equals to N square pi R square over 2R. Okay, now those R cancels. I'm left with 1R. Okay, so now we have a very different equation. Okay, if I rearrange this equation, what I'll have is R equals to 2L over mu naught N square pi. Okay, so I can substitute the values in, so I can have R equals to 2 times 15 times 10 to the power of -3. Why do I have 10 to the power of -3? Because the inductance is 15 millihenry, and I have mu naught, which is just the permeability, that is going to be 4 pi times 10 to the power of -7. I have 420 turns squared, and then I have pi. Okay. All right. So I can approximate pi to be 3.14. What I'm left with is my radius is going to be approximately 43.1 millimeter. Okay. So that's what I'm left with. And that would be my final answer. All right, moving on. We're at the end, so bear with me. Okay, the last of the electromagnetic block is going to be the AC circuit. All right. So let's look at the question. Let's read the question. A series RLC circuit attached to a power supply of peak voltage 140 volts. So peak voltage is equals to 140 volts with a power factor of 0.76. So my power factor is going to be my cos phi is simply going to be 0.76. Okay, and then from that equation I can say, I'll just write down there, IT is equals to 4.5 sine 20 pi t. So the important part here is to recognize that this is the peak current. Okay, and then now what I need to do is, the first thing I need to do is calculating the RMS current in the circuit. So for part 1, I know that my I peak is going to be my square root of 2 multiply with I RMS. Okay, so my I RMS is going to be my I peak over square root of 2. So my I peak is just 4.5, right, amps over square root of 2. What I'm left with is 3.182 amps. Now that's fairly simple enough, all right? Okay, so moving on to the part 2, calculating the value of resistance. Okay, so there's a point here that when we talk about AC systems, we talk about Ohm's law as well. It's just a slightly modified Ohm's law. Rather than having V equals to IR, we can have V equals to IZ. Okay, so generally you will find Z from XL, XC, and R. However, in this particular question, you can actually relate Z to R simply by recognizing that Z cos phi is equals to R. Okay, so put it in a diagram sort of place. I can have R, and then I can have probably XL minus XC, XL minus XC here, right? And then I have my Z over here, right? In a phasor diagram, that is. Can have phi between them. Okay, so this is the relationship that you sort of have to know. Okay, so once you know that, right, you can immediately substitute it into the modified Ohm's law, and I can have V equals to I, right, times R over cos phi. Okay, if I'm looking for R, right, I'll have R equals to V cos phi over I. Okay, so this particular V is just the peak voltage, so 140 times the 0.476 power factor, and then the I, which is again, if I use peak at the top, I'll have to use peak at the bottom, so I have 4.5 at the bottom, so I'm left with R equals to 23.64 ohm, and then that's my final answer for resistance. Okay, now for the last part of 5a, all right, we'll have 5b later on, but let's have the 5a3, right? So we are asked to calculate the impedance. So again, I have V peak, I can just have V peak equals to I peak times Z. Z is just the impedance, so Z equals to V peak over I peak. V peak 140, I peak to be 4.5. I'm left with an impedance of 31.11 ohm. Alright, and that's done. That is 5a. Now for the last of the last, right, we have the last question, question 5, then we have the last part of question 5, which is 5b. Right, let's calculate. Right, an inductor is connected in series to an AC voltage supply of 30 volts and frequency of 60 hertz. So I have the power supply, right, V equals to 30 volts. All right, and then I have my frequency to be 60 hertz, Now I have inductive reactance. So inductive reactance is XL. Induction L, alright, 98 ohm. Okay, I'm supposed to look for B1 inductance. So I have XL equals to 2 pi FL, right? So I know that my XL is 98, and I have 2 pi. I know my frequency is going to be 60, and then what I'm left with is looking for L. So L is simply going to be 98 over 120 pi, which is approximately 0.26 Henry. All right. Okay. So the last of the last of it, guys. All right. So 5B2. So B2. I'm looking for the peak current. So I know my peak current is simply going to be the square root of 2 multiplied by the VRMS. Okay. VRMS is very much supplied given here. VRMS. So I have my V peak is equals to square root of 2 times 30. Right. Oh, I do apologize. Okay, so I have the first relationship, which is V peak is equals to square root of 2 times VRMS, right? And that is going to be equals to my I peak times my XL, alright? And then I can look for the peak current, right? Because we know what the value of VRMS is, right? It's simply going to be the square root of um, 2 times the VRMS, which is 30 volts, right? Over my XL, which is 98, and that would leave me with a peak current of 0.433 amps. And that is my final answer for 5B2. Okay, and that is it. That is all of the questions from Pspm 2021, right, for the electromagnetism block. In the next video, I'll be discussing, or at least I'll be showing you the solutions for the optics block. Alright, so that just covers chapter 7 and chapter 8. I'll see you in the next video. Thank you very much.